your FTA may have gone through the same slides last Thursday. Then we'll move on to this week's topic. Right. One quick reminder is this Saturday we are going to have quiz 2. This time is 2 hours because we have tested it, and the last question requires more time. So I can't chop that question into smaller chunks. So simply let the test be 2 hours instead of 100 minutes. Alright, so give time for the last section, section 5. If you don't give enough time, you probably spend the last few minutes just reading the question without answering anything. So spend some time on it. Right? At least 40 minutes for section 5. And then I reserved about 5 marks difference between the best solution and second best solution. That requires some what I call aha moment. Once you get that, once you got the idea, you will get the 5 marks. I haven't teach you this. It actually can be derived from what you have learned so far. That requires some creativity to get that level. So for the rest, so I reserve 5 marks for that. Right? And don't forget, Form 1, Level 2 SR1 this Saturday. So this is right after public holiday on 26th, Hari Raya. Alright, I will continue from here. This is last week. We stopped here last week because I have problems with my laptop. Now let's just go through this last 10 slides of last week's material, counting paths on that. So if you have gone through your lab demo with your TA last Thursday, you have seen this actually. Let's just recap the whole idea one more time. So last week I have teach you 2 algorithms on DAG. So if the given graph is a directed acyclic graph, you can find shortest paths on it in a faster way. You can even find longest path on this DAG also in a fast manner, which is P plus E. Now I want to show you one more thing that you can do if your graph is a DAG. You can count how many paths are there between 2 vertices again in V plus E time or in linear time. So I have a graph here that shows my someone's life experience and all the choices that he or she has at certain junction of his life. For example, all people will start from birth, right? And then they go to school. After school, they have choice whether to go to university or just go and find work. When you are in university, you have choice whether to go to work after that or to take further degree after that. After you do PhD, most likely you can't prolong your stay in academia for too long unless you want to work like me, be a lecturer here. So no choice, you have to work. Right? For many people, we have to work first before we get married or stay single. For some people, even if you don't work, you can get married. So there is an age between 2 to 5 maybe. Okay? Then and so on. But eventually, all of us we cannot escape from what we vertex number 8 said. Eventually, all of us will die. So this is a DAG. Can you verify that this is a DAG? You can only move forward in time. You cannot go back. So once you move from school to undergrad, you can't repeat what you have chosen in vertex 1. Right? Once you decided to take PhD, you can't repeat your undergrad. Something like that. So you can only go forward in time. So there is never be any cycle in this life event graph. Right? So my question is, how many different possible lives that you can live if you have chosen different paths before? So my path is 0, 1, 2, 3, 4, 5, 7. I haven't reached vertex 8 yet because I'm still here, right? I'm still here. But most of you are currently 0, 1, 2. We are in vertex 2. Some of you already reached vertex 5. Or one of you actually already reached vertex 5. Okay, so how many different paths or how many different possible lives that you can live if you have this kind of DAG. Okay, you can have 0, 1, 2, 3, 4, 5, 7, 8. So let me draw some arrows here, some lines here. So I can go like this, right? Go down, go right. This is one path, right? One way from vertex 0 to vertex 8. But I can decide to split here. I don't want to get married. Like many of, you can look at the statistics of Singapore. Many people decided to do this. As your lecturer, I encourage you to get married and have kids. Really. Help your country. Produce babies. So go hit vertex 7. Anyway, back to track. So some other people decided not to do PhD. So from undergrad, where's my cursor? Oh, here. From undergrad, straightforwardly go to work, and then you can decide to go 5-7 or go 4-6. Right? And then some other people don't even do undergrad. Here, just go to work, and then either 5-7 or 4-6. The answer is there are 6 different ways. 6 different ways. Can you verify there are 6 different paths, possible paths from vertex 0 to vertex 8? Now that your task is to count them. How many of, if I give you a DAG, how many different paths are there between 2 vertices? How many different ways you can traverse between vertex 0, starting vertex, traversing some other vertices, ending in certain other vertices. Alright. So I'm going to show you 2 ways to do this systematically. So if you do it brute force manner, try all possible paths between 2 vertices, you can do it for small DAG, small text. But if I give you a slightly larger DAG, if you do it like this, you most likely you will be off by 1. I mean, your computation will be off, and you spend too much time repeating your drawing, verifying whether you don't miscount or overcount certain paths or not. So let's do it more systematically. Right? I'm going to show you 2 ways. The first one is the graph way, or bottom-up DP way. First, we call topological sort of this DAG, and we'll do something using this DAG, using this topological order. Right? So if we run the topo sort, we will get, for example, 0, 1, 2, 3, 4, 6, 5, 7, 8. This is one of the several valid topological order of this DAG. Now let's propagate some information. We say that the number of paths from vertex 0 to vertex 0 is one way. This is the first thing that we know. This is our base case. Right? And then we will follow these vertex numbers according to this topological order, and we will tell our neighbors how many paths that we have found so far up to that vertex. So vertex 0 tells vertex 1, hey, I know one way, so vertex 1 can increase the knowledge from 0 way to 1 way. The second vertex in topological order is vertex 1. So vertex 1 will propagate information to its neighbor, to vertex 2 and to vertex 4. So both vertex 2 and vertex 4 increase their knowledge. Now I know from 0 way to 1 way. Same thing with vertex 4, from 0 way to 1 way. Now I process vertex 2. Vertex 2 is here. Vertex 2 propagates information to its neighbor, vertex 3 and vertex 4. Vertex 3, hey, previously you have 0 way, now I have 1 way to reach vertex 3. Vertex 2 to 4, okay, vertex 4, now you have from 1 way previously, where? From 0, 1, 4, right? Now becomes 2 ways, from 0, 1, 2, 4. Right, we continue, vertex 3. Vertex 3 only have 1 neighbor, so it will tell the neighbor, which is vertex 4, from 2 ways, you now have 3 ways. Now I'm about to execute vertex 4. At this moment, I want you to notice something. When I want to propagate information for vertex 4, I know that the recorded ways is 3. Can you verify that 0, 4 really only have 3 different paths? You have 0, 1, 2, 3, 4, 0, 1, 2, 4, or 0, 1, 4. No other ways. 3, right? So when you start executing the certain vertex, you know for sure that you are propagating the correct information. You know how many paths coming to this vertex, And when you are about to process this vertex according to topological order, now is the time to do vertex 4, right? You know that here 3 ways. By telling your neighbors, I know 3 ways to come to me. By telling that your neighbors, you are always correct. You will never have to redo this. Okay? So vertex 4 tells vertex 5 and vertex 6, I know 3 ways. I know 3 ways. So vertex 5 increase number of knowledge from 0 to 3, 0 to 3. And 6 pass to 8, 5 pass to 7, and 7 pass to 8 also. So in total, when you reach vertex 8, there are 6 different ways. Alright, got it? So this is the systematic way. Find the topological order of that DAG, and then you start from one base case. You know that the number of ways from source to source is 1 way. And follow this order given by topological order. Tell your neighbors what you know. Keep repeating that. At the end of after all vertices have been processed, your target vertex will have the correct number of ways. This is what I call bottom up, starting from one base case, propagate information to the rest. However, we can also write the same solution in recursive manner. And with this example, I want to show you the difference between bottom up and top down. Just the one comparison between those two. So we can also solve the counting pattern in DAG with a recursion, with top-down DP, recursion with memo table. So I will declare a function, a recursive function, with one parameter. I call it numpath. Numpath I be the number of paths starting from I to ending vertex. Then I can have this recurrence relation. I can say the number of paths between T is the destination to itself, destination to destination, is 1. There's no other way. Right? Suppose you are in the destination already. No other way to reach destination other than that way, by saying that. So 1 way. Other than that, number of paths I will be the summation of number of paths J for all J adjacent to I. Picture, I can show how this works as in the next slide, as using animation. And then I will show that there will be recomputations if you don't store the previous result in a table. There will be recomputations. We want to avoid this. Right? So this is the code roughly. So if I have given you the recursive function name, the list of parameters, the list of base cases, and the list of recursive case, hopefully it is not too hard for you to translate it into something like this, where you have the recursive function, the parameters, the base cases. This one, the first line, ignore the second line for now. And then the recursive case is to sum all the numpaths for all adjacent vertex to this vertex. And then finally return that answer. Right. So this recursion will go something like this. What is the number of paths of vertex 0? Vertex 0 doesn't know at this moment. So if we recursively call its neighbor, what is the number of paths of vertex 1? Again, vertex 1 doesn't know, so it keep calling. 2 call to 1 call 2, 2 call 3, 3 call 4, 4 call 5, 5 call 7, 7 still don't know, 7 call 8. Alright, so this recursion goes like that. So what is the number of paths between vertex I to destination? If you don't know, what do? You go to recursive case, and so on. Okay, when you are in vertex 7, you call vertex 8. Vertex 8 is the destination. So it knows for sure there is 1 way to reach me, right? So you will tell the one who calls it, which is vertex 7, hey, vertex 7, number of ways 7 is 1. Because vertex 8 reports there is not 1 way to do it. So knowing that, vertex 7 reports to vertex 5, there is 1 way. 5 reports to 4, there is 1 way. However, 4 doesn't stop there. It has other neighbors, right? 4 have 6. But 6 doesn't know how many ways to reach 6. So it asks 8. 8 again reports there is 1 way. So 6 now knows that there is 1 way. 6 now reports to 4 there is 1 way. Together with this report, 1 way from 5, 1 way from 6, 4 knows that there are 2 ways. Right? So 4 will report that to number 3. 3 will report that to number 2. But number 2 is not yet done because number 2 has 4 as neighbors. Right? Okay, at this point, when vertex 2 call vertex 4 again, you are hitting the same sub-problem. What is number of paths bracket 4, right? What is number of paths starting from 4 ending in 8? If you don't store this information in elsewhere, in some table, what happens is you will repeat 4, 5, 7, 8, backtrack, and then 4, 6, 8, backtrack, and then report the same number 2 ways. So if we already store these 2 ways in certain table, we can simply report, from 4 there are 2 ways. So vertex 2 knows that there are 2 ways from coming back from 3 and 2 ways coming back from 4. There are a total of 4 ways. And then report that to number 1. But number 1 still not done yet because it has an age between 1 and 4. See that if I don't store that from 4 there are 2 ways to reach 8, I have to redo the whole thing, which I don't want to. Okay? If I already recorded that there are only 2 ways from 4 to 8, I can simply tell vertex 1 there are 2 ways. I don't recompute. So vertex 1 knows that there are 4 ways from coming back from 2, there are 2 ways coming back from 4, there are a total of 6 ways. Report 6 ways. Right? See that the way the information is processed is from destination back to source. Because recursion starts from source, but it will only know the answer when it hits base case, and then start combining the answers in this recursive case, so that the first caller, which is number of paths bracket 0, knows what's the answer, which is 6. And this is how recursion behaves. See that the answer late at the end is found here, whereas in the previous slide, this one, the answer is found at vertex 8, the destination. Now bottom up and top down, do you see that they are behaving slightly different in terms of order of passing information, the way the information is passed? Right? So both of them are equally good and produce the same answer, just that they compute the answer slightly different. So this is just a preview of dynamic programming. Can you give me a feeling of what's happening so far down there? Right? Manageable, scary, very scary. 10 versus 9, half. Alright. Okay, let's strengthen this concept with the second lecture. Right. Hey, so okay, we are done with the first part. Quick reminder for those who came late. This Saturday, there will be quiz 2. It is going to be harder and longer than quiz 1, so be prepared for that. Right, so we'll continue with the today's lecture. In about 40 minutes until 11, I have estimated it's about 40 minutes. I will discuss the first part of this lecture, algorithms on implicit DAG. This is the fun part. If I give you the DAG straightforwardly, the problem is too easy, according to my opinion. Because I have teach you three algorithms on DAG. You can find shortest path on it, you can find longest path on it, you can count how many paths on it easily. Right? Just find a topo sort and do something with that topological order. But to make it interesting, I will hide the DAG from you. I will not tell that this problem has a DAG behind. So you have to find a DAG. Like in part 2 of the class, I want you to find the graph, the general graph hidden in the problem description. Now I want you to find the DAG hidden in the problem description. So that's why I said it's implicit. Okay, so dynamic programming algorithms, it can be written in bottom up and top down. If you choose the top down version, which I'm going to use for most of the example here, you will need to write a recursive formulation, a recursive function. And a recursive function cannot have cycle. Otherwise your recursive function cannot terminate. So your recursive function must end in a base case, and you can't have a case where function A call function B call function A again, and it never stops. If you have that kind of thing, your recurrence doesn't work. Right? So we will see some problems have simplifying assumptions so that we can transform the problem from some other form into a DAG. So the key point of this lecture, after listening to these 3 examples, 2 in the first 40 minutes and 1 more later for your PS7, you will see that you can convert something that is in general graph, can contain some cycle. You can transform it into a DAG, something that has no cycle. So I repeat, the initial problem given to you will be something that has cycle, can be general graph that contains some cycle. You can do something with it so that it turns out to be a DAG. And once you can convert it into DAG, you can apply the algorithm that you learned last week to solve it. Okay. But before that, quick revision from last week's material. LIS, longest increasing subsequence. Tell me, what is the LIS of 8364577? Increasing, strictly increasing. I saw at least 18 clickers, so hopefully it is more than that. I have 50 students who have, I know that there are 50 students who have clickers, so this number is much lower than that. Okay, 22, slightly better than previously. Okay. If you bring your clicker, take it out. Okay, between 3 or 4, between what? Between 3 or 4 here, or even 5. The answer is 4. You can do this, there are 2 ways of doing this. If the LI is quite small, you can use your brain power. You can use your brain power, brute force that, look at some pattern, find a longer one. When it is quite long, like 20 numbers, don't do brute force. You do brute force, most likely you will be off by 1 or wrong. And even too slow for that. So you have to do it systematically. So here, in a glance, you can see that 3, 4, 5, 7 is increasing. Can your eyes spot that easily? 3, 4, 5, 7. You can immediately look at those numbers. Some parts of the numbers are increasing. 3, 4, 5, 7. It's 4 already. So there are 7 numbers here. 4 of them are increasing already. Then you ask yourself, can you make it 5? Can you make it longer? 3, 4, 5, 7, 7. The last 2 7 are not increasing. So the limit is more or less 4. So the answer 4. Next. I can change the problem a bit from increasing to non-decreasing. Simple switch. So can you tell me what's the answer? I'm looking for a subsequence that is non-decreasing and the longest of such subsequence. Very easy. There were 22 responses just now. I said it's very easy. Very, very easy. Everyone? Yes, it's 5. So just now I say 3, 4, 5, 7, 7, right? And 7, 7 is not decreasing. It stays. So you can extend by 1 more, make it 3, 4, 5, 7, 7. That is 5. Next. So if you have seen lab demos, this shouldn't be that problematic. So I want to go from 0, 0. 0, 0 is top left. I want to go to 3, 3. How many ways? In last lab demo, if it's only 3, 3, the answer is 6. But now it's 4, 4. So how? And if you look at last year's final exam, I gave 5, 5. Yeah. So can you do it quickly? If you don't do it the way I teach you, the way that the algorithm on next strategy, you will spend I don't know how many minutes trying to draw lots of heads. If you do it systematically, if you know what I'm asking about, you can apply the algorithms on DAG. Then you can find this systematically in just 16 steps. 16 is number of rows times number of columns. C plus E. You can do it in 16 steps. So how? Those who haven't tried this or those who haven't done lab demo, I mean, you listen to lab demo but they never tried this before, I suggest that you do it because I'm planning to do similar thing in today's, either in quiz 2 or final exam. It's called applying manual dynamic programming to help yourself in certain manual situations. So you don't have computers, you have to solve some combinatoric problems that has overlapping sub-problems. If you do it brute force manner, it's going to be very slow. But if you know that there is a systematic way of doing this, and you follow that strategy, it will be much simpler. It's between exponential complexity to several steps only. 22 just now? 2 more? Okay. 20. For those who didn't get it wrong, those who got it wrong, can you repeat the process that I teach you just now? You put 1 on the top left corner and tell that to your neighbor, 1, 1. And then here, you tell to your neighbor, 1, 1. Here, you tell your neighbor, 1, 1. Okay? Here, you don't have right neighbor, so you only tell your downwards neighbor, 1. Then here, you tell 1, 1. So this becomes 2. 1, 1 becomes 2, right? And then 2 tells this, 2 plus 1, 3, right? And then 3 tells 1, 3, 1, 2 tells 1, 3. 3 from me, 1 from above for 4, right? You keep doing this. So in 16 steps, you will get at 3, 3, 20. If I give you 5, 5, it's much harder, right? I give you 10, 10. 10, 10 is 100 steps, too many. For exams, I think it's too many. 5, 5 is reasonable, about 25 calculations. Right. So do it. Try to do it manually. Try to be able to do this kind of exercise manually. Right. So I'm going to show you 2 examples where initially the given problem either gives you the graph or don't. This graph has cycle in it, and because it has cycle, we cannot apply our algorithms on DAG that we learned last week. So, but there will be some simplifying assumptions that we can use. If we use that, the graph inside the problem can be transformed into DAG. And once it becomes DAG, you can do last week's algorithm. You can use last week's algorithm. Traveling salesman version 1. Okay, so look at this problem. There are C cities, and there is one salesman starting sales tour from a certain city S, and this salesman can end his sales tour at any city labeled with E. So for example, I have this graph, 3 vertices. If the salesman starts at vertex 0, he can end at vertex E, vertex 1 or vertex 2. Both of them are labeled as possible ending vertex, possible ending cities. Now, he wants to visit many cities to sell his goods. Every time he goes from vertex U to vertex V, he obtains a profit UV. And then there is a definition saying that staying in the same city is 0. So this salesman has to keep traveling. The question is, what's the maximum profit that he can get? And the profit is shown as the weight of each UV. So 0 to 1, if the salesman go from 0 to 1, he will get profit of $3. Something like that. I'll give you a question. What is the maximum profit that he can get on this test case? He starts from vertex 0, he can end at vertex 1 or vertex 2, and every time he moves, he gets money. The question is, what's the maximum profit that this salesman can get on this graph? I need your participation. So even if you feel that if you bring clickers, don't hesitate to click. I know that there are at least 22, hopefully more people with clickers here. I predict around 70, 80 students here, and hopefully more than 20 with clickers. So if you bring clickers, take it out and use it. Okay. Okay, good. I'm happy. Yes. If this answer is haywire, I have to redo my previous lectures. Hey. So if you have a graph with no negative cycle like this, no negative cycle, right? It's good for status path. But here you don't have negative cycle, but you can have positive cycle, right? And the question is maximum profit. So last week I already told this, right? If you are doing a longest path on a general graph, if you spot any positive cycle, you can keep cycling there and get infinite profit. So salesman can go 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2 infinitely, and then got infinite profit, and then finish his tour in either 1 or 2, get infinite money, become the wealthiest man on earth. It's impossible, right? The problem is not like that. Okay, so if you are if the problem is changed from finding if I restrict the problem to finding longest simple path, and this is the explanation of what I said just now. This graph has a positive cycle, so you can keep cycling there to get infinite money, right? So the longest non-simple path from source to any vertex E will have infinite weight, because you can take any positive weight cycle to get infinity. Alright, however, if I reword the problem, the salesman can go to any cities, but it cannot repeat cities. So if you have 0, 1, 2, 0, 1, 2, you have 0, 1, 2, 0. Vertex 0 is repeated, right? If you have that, the path becomes non-simple. A simple path is if you don't have repetition. So if I ask the problem a bit, change the problem a bit, I want the longest simple path. So this salesman can never repeat vertices. That wording implies that there is no cycle. It cannot be cyclic. So 0, 1, 2, you cannot go back to 0. 0, 2, 1, you cannot go back to 0. Something like that. So if the problem is changed like that, then there is an answer. Vertex from s equals to 0 to any of the E, the best way is 0 to 1. 0 to 1. You will get 5 plus 2 or $7. If you go 0, 3 and then stop there, you only get $3. If you go 0, 3, 2, 3 plus 1, $4. If you go 0, 2, stop there, you only have 5. So the longest simple path from 0, vertex 0 to any of the ending vertices is 0 to 1, which is 7. However, to find this, you will need brute force. You need to try all possible ways. And this is hard. Later, at the end of this lecture, I will show you that if you do backtracking on the third example, it's going to be very slow. Oh, this is hard. This is still a hard problem. However, this problem, UVS 10702, actually has one extra parameter, and this extra parameter I didn't tell you beforehand. But when I tell you this, I will show you that with this information, the graph is actually acyclic. So the problem says that the salesman can only make T intercity travels. So there is one more constraint given in the problem description. And by using this information, we can transform the graph into a DAG. So if you can only make T intercity travels, in other words, in a valid tour, the salesman must arrive at an ending vertex after T steps. So his T step, he must be in a city that is classified as potential ending vertex. If it's not, you cannot stop there. So the key step is to attach one more information to each vertex. When you are in that vertex, how many intercity travel that you have left? You add that one extra thing. If you add one extra thing to every vertex, your vertex becomes a pair. Right? Previously, you only have vertex number. Now you want to add one more additional information for each vertex. For each vertex, you want to know if I'm here at this point of time, how many intercity travel that I can still do. Initially, you will be 0, 2, right? 0, 2 means that you are in vertex 0. You can still do more, 2 more travel. Or suppose T is equal to 2. At the moment, at the very beginning, you can do 2 steps. Right? So you are in vertex 0, you still have 2 steps left. At vertex 0, you have 2 choices in the original graph. Go 0, 1 or go 0, 2. If you go 0, 1, you will be in vertex 1, and the number of intercity travel that you can do is 1 less. From 2 down to 1, so you will be in vertex 1, 1, right? You are now in vertex 1. The first item in the pair is which vertex you are on. The second information in the pair is how many intercity travel that you can still do from this point onwards. Right? If from source you go 0, 2, you are now in vertex 2, again with 1 less intercity travels to be made. Okay, now look at 1, 1. At 1, 1, you are here, right? You are here. You have 2 choices. Either you go back to vertex 0, or you continue to vertex 2. If you go back to vertex 0, you will get plus $5. You are now in vertex 0 again, but you have 0 intercity travels left. See that attaching the second parameter transform this problem from going cycle from 0, 1, 0 into 0, 2, 1, 1 and 0, 0, and these are 3 different vertices, right? 3 different vertices. So no cycle, right? Even though you in the original graph you go 0, 1, 0, here actually 0, 2 go to 1, 1 go to 0, 0. However, you cannot end in vertex 0. So this is actually an invalid ending vertex. So at 1, 1 you can go to 2, 0. Right? How? From at 1, 1 here you can go to vertex 2 by getting $1 more, and you are now in vertex 0 at vertex 2 with 0 intercity travels left. Same thing for 2, 1. You can go to 0, 0 or go to 1, 0. Alright. Now, can you see the graph on the right is a DAG? It's directed and it's acyclic. And you can prove that it's acyclic very easily. The intercity travels always decrease. So as you go, if you look at it column by column, this one, as you move forward to the right, the second parameter 2 go to 1, go to 0, you will always decrease. Can you see that if you draw the DAG this way, if you go to right, you can never go back to left. Because as you move, you will decrease the intercity travel by -1. Right? So we have verified this is a DAG. Right. Then, what's the problem that we are solving now? We want maximum profit. Can we find a weighted path that is longest here, so that when we total the profit is the maximum? Longest path, right? So you start from 0, 2, you find longest path on this DAG. However, you have to prune those invalid ones. For example, the longest path from 0, 0 to 2, 0 will be 4, right? The longest path from 0, 2 to 0, 0, 0 will be 5, 9, which is 14, right? However, this is an invalid ending vertex, so we don't choose this one. 0, 2 to 1, 0 is 5 plus 2, 7, and this is larger than 4 just now, so this is our final answer. So after we run longest path, we check all the ending vertices with comma 0, we find those with the largest final value. That's our answer. And where's the DP? DAG doesn't, although it's acyclic, it can have many edges coming to the same vertex. So imagine that, for example, after 0, 0, that suppose after this vertex there is some other things on the right. So see that you can go like this and then to the right, or from bottom and then to the right. This 0, 0 will be repeated twice if you have that situation. So later you will see that by recording previous computations, you will save time. On this example, it's not clearly shown. On the next few examples, it will be much more clearer. But the idea is from something that has cycles, you can attach one information here, you can transform the problem into something that is acyclic. When it becomes a DAG, things become much simpler. Okay, some quick note about longest path problem on DAG. Again, like last week, I say that there is no non-simple path in a DAG. Every path will be simple because you can't ever repeat. You can never cycle in a acyclic graph. So when we say SSLP on DAG, we never mention whether it's simple path or non-simple path because there is no difference. However, when we are dealing with general graph, usually people will call what is the single source longest simple path on this general graph. Because if the word simple is dropped, becomes non-simple, and that general graph has cycle, the answer is always positive infinity. Got it? However, if you put simple here, there will be an answer, but to find the answer is hard. Okay, so we have seen this before. You find the topological sort, stretch it, or you can write the recursion for this. Okay, I will show you that now it is slightly easier to do it in recursive manner. Because if you want to do it in bottom-up manner, to find topological order of this guy, of this DAG, it's a bit harder. Actually, you can spot the pattern, but with more parameters, it's harder to build the graph and find the DAG on it, the topological sort of it. So, for this lecture onwards, especially for this lecture, I will show you how to write recursive solutions for these three examples. I want to use this to strengthen the concept of recursion. If I do it in topological order manner, you don't see recursion there. So I don't want that one. I want to show you recursive solution for these three problems. Right. So now the number of vertices in your DAG increase, not just C cities, but C times T. Right? Because you can have a pair now, and by the number of vertices there will be C times T. So we can solve this problem using recursive formulation. We can say give a name get profit, and usually one of the parameter is where you are now, and then the second parameter will be the additional information that you want to give to this vertex. You want to attach to this vertex, and then define this as the maximum profit that the salesman can get when you are in certain vertex U. You still have T underscore left number of steps to go. Okay, obviously now we need to think about base cases. So what are the base cases? Okay, so if T underscore left is still positive number, do you realize that you can still move and get more profit? Right? So we don't care when T greater left, T underscore left is still greater than 0. It's not our time to stop yet, for this salesman to stop yet. So, however, when T underscore left is really 0, the salesman has two possibilities. When a vertex U is labeled as possible ending vertex. If it is true, then get profit U, T left is 0. You can end your tour there. Other than that, if you don't have move left, but CTU is not a valid ending vertex, you need to say get profit U T left will be minus infinity. To say to the one calling this recursive function, going here is a wrong step. Something like that. You give a very low negative value. Because it's a maximizing problem, right? You want the higher one, right? By giving a very low negative value, you tell the one who calls this recursive function, going here is wrong. Now, let's see what happens when t underscore left is a positive number. Means that you can still move. You will move to the one which gives you the highest profit. How? You can have, from vertex u, you have p element 0 to c minus 1. You can have p neighbors, p minus 1 neighbors. If you go to that neighbor p, you will get this profit, and you will recursively go to, you are now in vertex v, you have t left minus 1. This is your recursive formulation. At a certain vertex with t positive number of moves left, you look at your neighbors. If I decided to go there, I will get that profit. I will recursively be in that city now with t minus 1 intercity travels left. And I will let my recursion repeat the whole process. Out of these choices, one of these will give me the maximum profit. So I will take the max out of these p minus 1 choices. Definitely you cannot stay in your own city, right? Because profit u comma u is, u bracket u is 0. You have to move. Okay, so you can transform that into a simple code like this. Get profit where you are, how many moves left. If d left equals to 0, you say, you check whether can you end in this vertex. If yes, you don't have to, you will not get any more profit, but it's a valid ending point. Other than that, it's a negative infinity. It's to say that I don't favor going here. And then here, other than that, I will look at my neighbor from 1 to c. Oh, it's 1 to c, not 0 to c. Change this to 1 to c. Vertex number is starting from 1. Okay. So 1 to c. Get that profit. Get that profit, and I will recursively go to this vertex with t left minus 1. One of this gives me the maximum profit. To avoid recomputations, I will provide a table that tells me whether u comma t left has been computed before or not. If it has been computed before, I will simply return it. Other than that, I will compute this and store the results here. Once you have this DB solution, you can do analysis easily. So if your DB is not a complicated one, a standard one, we can analyze the time complexity very easily by asking several questions. How many distinct states are there in the problem? Or if you want to talk in graph terminology, how many vertices are there in your DAG? The answer is c times t. Originally you have c vertices, right? Every vertex you have t minus 1, t minus 2, blah 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 until 0. T copies of that vertex. It becomes c times t. And then you have to ask what is the time needed to compute one distinct state. Every state or every vertex, you need to look at c neighbors, right? So c neighbors, actually c minus 1, but it's still OC. And the third question is, what is the overall time complexity? So if you have overall time complexity, or in other words, the total number of edges in the DAG is how many vertex that you have in your DAG and how many outgoing edges are there for every vertex. So if this vertex has C edges, this vertex has C edges, this vertex has C edges, and there are C plus C times C such vertices. The overall time complexity will be C times C times C, or C squared times C. This is time complexity of the dynamic organism. Right. Since that it's better to stop here, let you digest. We'll continue at 10:57. If you have questions related to the first example, you can come forward and ask me. The second one will be slightly similar with the first example. Yes. Yep. Okay, let's continue. This is PS7R. Look at the timing. This will be auto open on Jane's first birthday, which is tonight, midnight. And hopefully I can touch a bit of of the last example, referring salesman problem. Hopefully I can cover enough so that whoever wants to start this quickly can do it as soon as tonight. This is hard, especially for 2010R students. I believe you haven't seen this kind of question before. However, after enough discussions, sooner or later, once some of you spotted that keyword, it becomes much easier. Okay? And this is the current leaderboard. There are gaps between level 10 and level 9. But the speed of your present leaderboard is somehow also determined by the speed of your TA. So can you also encourage your TA, hey, I want to be in the leaderboard, can you grade my PSS quicker? Something like that. Okay, we continue with second example, only 5 slides. I want to give you another example, quite simple. That initially the problem given to you has funny looking graph, and maybe you don't have any idea how to solve it. But then after looking at certain constraints, you realize that it can be transformed into a DAG. So there is a game like this. You are given n vertices up to 26 labeled from A to Z, so up to 26 alphabets. Some of them are special are drawn with double circle. So for example, vertex C here drawn in double circle is a special vertex. So each vertex has exactly 2 outgoing edges. One that has label 0 and then one that has label 1. The edge may be a self loop. This is something that I didn't teach earlier. We always tell ourselves the given graph are simple graph. Simple graph means no self loop. Between pair of vertices there is no 2 multiple edges, only one edge. And here we have vertex E, for example, that it's looping itself from E goes outside, coming back to E, from E outside, coming back to E. Same thing with D here. And also we have cycle A, B, C, A. We have cycle. So we have cycle, we have self loop, problematic. So as soon as you have a self loop, this is no longer a simple graph. We like simple graph because with simple graph, we can do some other analysis easier. For example, in a simple graph, you can have at most p-square edges. Because in a simple graph, the most dense graph that you can make out of it is a complete graph. And a complete graph has at most p-square vertices, p-square edges. And you can use that for many other analysis. But here, if we don't restrict that, you can have a single vertex having thousands of edges that are looping itself if the graph is not simple. So problematic, right? So the analysis becomes more problematic. Right. However, in this problem, we are having some other constraint that helps us transform this funny looking graph into something that is much more familiar for us. The question is how many ways to reach the special vertices from vertex A, so the source is vertex A, in exactly m moves, and m is small. So can you continue the drill? You know that you can only use at most m edges. You can only move m times. So can you attach this information to every vertex? It turns out that you can, right? So if we don't convert the multigraph, you will have infinite loop like A, E, A, E, R. Okay. A, E cycling around. You take either H will be infinite, right? Taking either H between this self loop or this other self loop, you will stuck in E. You will stuck forever in E. Right? Originally, it's counting how many paths are there, because the question is how many ways, right? From source A to special vertex C here. Originally counting paths on general multigraph. But after conversion, after adding one more information, how many moves left? becomes a counting path on actually non-simple DAG. But even though it's non-simple, we don't care because there is no cycle. Let's take a look. I will attach comma 2. Suppose m equals to 2. Means that from source vertex A, I can move 2 times. I put A comma 2. I can go where? I can go to B. I can go to E, right? I can go to B by following H label 0 here. I will be in B. I have one move left. Or I can go from A comma 2. I can go to E by taking this H, right? I will be in E. I have one move left. Now you are in E. Whichever H that you take, you will be in E comma 0, right? But from here, can you still continue? No, because you already have 0 moves left. If you don't attach that information, if you don't have that information, when you are in vertex A, do you know whether you have to stop or not? You don't know because because if you take 0, you come back to E. You can take vertex 1, come back to E. Self loop may be easy to detect. You can ignore self loop. However, what if E go to B, E go to Z, Z back to E? Can you detect that you are going to cycle eventually? How about if E go to X, X go to Y, Y go to Z, Z go to E again? Can you detect that? By attaching this information, you know for sure that once your number of moves available runs out, your number of moves equals to 0, you can simply stop there. Now look at B. B comma 1, we are here now. You can have two choices, go down to D or go right to C, right? If I go down to C, I will be in C, no moves left. If I go down, if I go to D, I will be in D, I have no move left. And this is my only, this is my DAG. If I have M equals to 2, starting from A. Can you see that there is no cycle at all on the picture on the right? No cycle at all here. And how many ways from A comma 2 to C comma 0? How many ways? Only one way. So the answer is 1. This is a counting path on non-simple DAG. We can use the algorithms shown earlier, just now, at the beginning of this lecture. We can write this in recursive format, ways U comma M left. So at the beginning of this lecture, when I repeat last week's notes, I have numpath brackets I, right, one parameter, where I is the vertex number. Here I have ways U is the vertex number, comma M left. So the additional thing is comma M left, right? This is the only additional thing. So let this be the number of ways to reach any special vertex or reach destination from vertex U with M underscore left number of moves to go. If I don't have any move left, I check whether the one that I'm standing on is a special vertex. If it is, I have one way. If it's not, I don't count. This is not a valid way, 0 way. Other than that, I combine the number of ways if I take label H label 0 or if I take H label 1. I only have 2 outgoing edges per vertex. Right? And I want to show you with this line, I want to show you that I can come up with another graph data structure. If I know that for every vertex, I'm going to have at most 2 outgoing edges. One is labeled as H0, the other is labeled as H1. I can have two rows of 1D array. That simply tells me if I'm in this vertex, if I take H label 0, where will I go next? Where will I be next? If I'm in this vertex, if I take H with label 1, where will I be next? So I just need 2 one-dimensional arrays. I don't need a adjacency matrix. I just need two rows. Okay? So it's like a simplified version of adjacency matrix. Do you realize that? You know for sure that you only have 2 outgoing edges. Another kind of graph data structure. So we can write a very short recursive function as simply do this. If m left equals to 0, check whether it's special. If it's special, one way, other than that, 0 way. Then, if it's recursive case, if we sum number of ways, if we take h with label 0 and decrease m left, or we take h with label 1, if we decrease m left. Previously, this is a for loop, right? Because you have can go up to several neighbors. But here, you know for sure you only have 2 neighbors. So you just need to call this twice. Then you store this in a memo table so you don't repeat. Again, quick analysis. What is the number of distinct states, or what are the number of vertices in your converted DAG? 26 times m, right? Up to 26 times m, or number of vertices times m. Because for every vertex, you will attach how many moves you can make at that point of time. What is the time to compute one state? Just O1, because you know for sure for every vertex there are 2. So the constant is a constant factor. Previously, in the previous example, from every vertex you have at most c neighbors. But here for every vertex you know there are always at most 2. So you multiply these two together, n times m times 1 and n. Okay. So far, what's your feeling? Okay, good. Majority more or less there. So details we can fix up. We can fill in the details. We still have about one more month until the final exam. So DP will not be tested anywhere in quiz 2. Quiz 2 will stop at shorter spread, week 8. Right. Right. So this is for your PS7. So if you want to solve PS7, you have to listen to this carefully. PS7, no secret, is about traveling salesman. The original traveling salesman, not the one shown in the first example. So the one shown in the first example is traveling salesman that it can only make P intercity travel. That one is a special case. Now we want to deal with the original traveling salesman problem. So you are given a list of VCDs and P choose 2 pairwise distances. It's a complete weighted graph. This is a general graph. This is the same analysis that I mentioned just now. If you have a simple graph means no repetition. You cannot have self loop or multiple edges. You can only have P choose 2 or P square pairwise edges. Okay. It's a complete weighted graph, right? Yeah. So your task is to find a shortest tour that visits each city, all of them, exactly once. So that your tour will have exactly 3 edges, starting from, means a simple tour. You cannot have A go to B, B go to A again, go to B, go to A. You cannot do that. You need to go from A, go to B, go to C, blah, 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 visit all other vertices, and then finally come back to A. So the only vertex that is allowed to be repeated is the starting vertex. The starting vertex, go to all other P minus 1 vertices, finally come back to vertex A. Something like that. The only vertex that is allowed to be repeated is the starting one. We want a tour. 2 master and n is same thing. This is different from the previous example. The difference is I don't limit this to P intercity travels. Right? I don't. But and then I give a complete weighted graph. Means that from every vertex I can go to any P minus 1 other neighbors. So I want to ask you to do a simple test. I want to check your understanding of this definition. I give you this complete weighted graph. So this is a complete graph, 4 vertices with 6 edges, right? 4 choose 2 is 6. All of them have weight. AB is 20, say 20 minutes. AD is 35 minutes. BD is 34 minutes. My question is, what's the shortest tour that I can make if I start from vertex A, go all the way and come back to A. At the I tell you that between option 1 and 2 is the optimal one. Can you do a quick calculation and tell me whether the first option or the second option is the better one? Do it quickly. A, B, C, D, A is one tour, right? It's one tour that visits all 4 vertices, starting with A, visit all other 3 vertices, and coming back to A. But I can also do A, C, B, D, A. Will that give me different numbers? It's also a valid tour. It starts from A, visiting C, B, and D, or the other 3 vertices, and come back to A. What is the cost for the first one? What is the cost for the second one? Which one is shorter? Okay, 20. To be majority should go equal. Okay, good. You can count. Yeah, 97, right? The other one, I forgot, it should be greater than 97. However, can you be sure that between these two is the optimal if I don't tell you? No, right? You have to check all of them. You have to check all possible tours and say which one is actually the shortest before you can be convinced you cannot do better than this. So tell me, how many possible tours are there if I give you a traveling salesman problem with P cities? How many possible tours that you can make? That you can have? Just now I only show you 2. I said one of them is the optimal. But what if I say, I show you these 2, I don't guarantee whether these 2 contain the optimal one. If it's not one of them, can you tell me what's the optimal? If I rephrase the question that way, what should you do? Only half of you got it correct. You have to do phi, actually phi minus 1, check. Because you fix yourself, you start from A, right? But can you see that you can permute the other 3? Can go, you have A, B, C, D, right? You fix the first one. You always start from A and you want to end with A. But you can permute the other 3. So you can go A, B, C, D, 1. Right? A, B, D, C, back to A. Or A, C, D, D. A, C, D, B. 4 already, right? And then A, D, B, C. A, D, C, D. Do you realize that what I'm doing is enumerating 3 factorial, 6 other ways of permuting 3 numbers, 3 vertices. You have to do it 6 times. So here I only gave you 2 options. You have to examine the other 4 options. Among the 6, you need to figure out that option 1 is the one with the smallest. Then you can be sure the answer is 97. The length of shortest tool is 97. So because phi minus 1 is approximately phi, so it's a phi factorial. By the way, if you don't know why there is a factorial, it's the number of ways to count permutations. The number of possible permutation of phi objects is phi factorial. Hopefully you still remember that from 1 to 31. Or if you don't, like this I'm telling you now. Number of possible permutation of phi objects is phi factorial. So how big is 10 factorial? You can check your calculators. You can type in 10 times 8, 10 times 9 times 8, blah 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 until 1. Or if your calculator has a factorial function, you can punch those 1, 0, punch the factorial button, you'll get some number. That number should be 3 million, 3.6. What is 100 factorial? Can any of your calculator compute the number correctly? 25, so 26. So actually, some of you bring more than 20 bring recursion. Exponent 157. You are guessing that this is the correct answer, right? What if I give you two options that look very similar? One is 157, one is power 155. So which one is correct? You cannot guess. So what I want to say is factorial grows very quickly. So for PS7, I have, for PS7R, I have n equals to, and p equals to 1000. So all the best. 1000, not 100, 1000. Okay? So PS7R is n number of vertices involved is 1000. Alright. So the brute force or naive solution is in sketch is to try all p factorial permutations, pick the one with minimum cost. So with these two, with this slide, I want to highlight exam answering strategy that if you run out of time versus if you have enough time. If I ask you to find the solution for traveling salesman, giving me these two lines get you some marks. It's not wrong. Look at this. Try all p factorial permutations, pick the one with the minimum cost. It's correct strategy, right? It's a correct algorithm. Since I allow you to use pseudocode, giving answers like this can get marks. However, this is too coarse. Because I'm going to keep asking you, how can you derive permutations? How to generate the permutation in the first place? It's a very big step, actually. Right, it's a very big step. And then, which I'm going to show later. So the code, when you say try all permutations, it is big steps involved here. So in exams, since I allow you to use pseudocode, if you run out of time, don't leave it blank. Write something like this. But you will get marks, but not the full mark. But once you have time, you have to explain, elaborate things that what your intention is. You have to make sure that your words are easily implementable in Java. When I say using pseudocode, doesn't mean that you can write the algorithm idea in 2 lines like this. So as far as you can, try to provide more details. Okay, so details for just a bit digress to quiz 2. If you want to use certain algorithms that we discussed in class verbatim without changing anything, you can say, I'm going to use depth first search for this. You can just quote the name depth first search without telling me anything. I'm perfectly fine because you are quoting the same algorithm discussed in class. However, if like this, try all p factorial permutation using brute force. You have to say that I will modify depth first search by doing something. Then you have to say something, what are the changes that you make. I have to say the changes. Otherwise, if you say, I'm going to use modified depth first search, full stop. What kind of modifications, right? Because several modifications can lead to different variants of depth first search. Alright, so in the next slide, in the next example, I will show you how I can convert simple depth first search into a pure backtracking routine that tries all possible permutations. Right. Before I go to the code, I will give you the idea. Right. So depth first search, if you run it, even on a complete graph, it will run in p plus e, where e here is n, when p equals to n, number of cities, e equals to n squared. I don't need this slide. I don't need this. This is confusing for myself. Okay. you don't need this line. You just say E equals to C squared. E equals to C squared. So if P plus E becomes P squared. Because the input given to you is a complete graph, right? Complete weighted graph. And the adjacency matrix of phi rows, phi columns as a table. And you, if you run depth first search on vertex A, you will go to A, B, C, D, and then stop in phi square times. Because that's how depth first search works. Now I want to show you how to change something very minor in depth first search, so that if I do that, depth first search can try all possible permutations. And by doing so, turning a phi square depth first search that finds the depth first spanning tree, one path, into a phi factorial algorithm where I can explore all phi factorial tours. What I do is simple. When depth first search use a visited Boolean array, right? 1D Boolean array visited that shows depth first search if I have touched this vertex before, the next call of depth first search will never redo that thing. Now what I'm going to do is, when I want to exit recursion, I will turn off this information. I will say, in the future you can still use this vertex again. I'm just going to do that. And by doing that, my depth first search becomes awfully slow, but then it explores all permutations. It is called backtracking. It's called backtracking. And what we are doing is essentially, in the background, converting your general graph, which is a complete weighted graph, into a DAG, subconsciously, where each vertex now has one more parameter, and that parameter is this visited flag, or this visited flag, the set of vertices that you have visited so far. You will get something like this. Okay. So, if you run depth first search from A, you will flag A as visited and recursively go to B. And then you will flag B as visited and recursively go to C. If you order the vertices in that order. And then you flag C as visited and you go to D. At D you have no other choice, so you have to go back to A, right? And then depth first search, since everything has been visited, you backtrack, done. But you only have one path, A, B, C, D. Stop. That is the original depth first search. However, what I'm going to do now is when I exit, so when, for example, A, let me have an annotation here. A visited, yes, go to B. So I take this H2 here. Maybe use different color. I go this. Okay. And then depth first search say visit B. Okay, B done. Go to C. Why? Because I ordered the vertex number that way. Visit C. Yep. Okay. Go there. Go to D. D has no choice but to go back to A. So I have the first tour, A, B, C, D, A, right? I get some number. What is the total length so far? Now, when I backtrack, I will undo that I have visited D. So just now I said D is done, but I'm going to undo that. I'm going to undo this. How? I'm going to remove that flag. And I'm going to backtrack here. When I'm in C, I look at my neighbor. I have just visited D, so there's no point going here again. But A and B are still visited, so I'm not supposed to go there yet. So C also have no choice. So I backtrack. When I backtrack, I delete this and I backtrack. Now, when I'm in B, I realize that, hey, I have done with C just now, but D is now have visited flag equals to false. So I can go there. So I go there. Mark this as visited. D has no choice but to go to C. Mark this as visited. See that now you have tour A, B, D, C, and finally CA. You have a second tour. At the moment, no choice again, you backtrack. When you backtrack, you will erase this, backtrack, erase this, erase this. Here at B, you just now you have done C, you have done D, so you have no choice, right? You backtrack, but you erase that information. Here, you realize that I can insert. I've just come back from B. I can go AC first and start all permutations starting with AC, and then finally all permutations starting from AD. That's the effect of toggling off digital flag at the end of the recursion. So this trick is because of experience in programming context. I like to start with classical algorithm, and I only modify some bit to change it to something else. I don't teach you totally new backtracking algorithm. Right? It's just depth first search, redo something with that to make it do something else. Okay? So essentially what you are doing is to attach vertex information, visited information in each vertex. So when you are in vertex A, you know you have visited vertex A. You have three other options. You can go to AB, you can go to AC, you can go to AD. Each of them have different costs. When you go to AB, when you go to B, you know that you have visited A and B. A is where you come from, and then B is now, right? Knowing that you have visited AB, say that you only have two outgoing edges. You can only go to C or go to D. If you choose to go to C, you get 30. You have to use 30 units of time, for example. You are now in C, having visited A, B, and C. Having visited A, B, and C means that you have no choice but to go to D. Right? And then from here, B, A, B, you can also go to D. When you go to D, you have visited A, B, and D. You haven't visited C. Means that the next edge will be going to C. Alright, look at this. The state D, having visited A, B, C, D, can be visited from other ways. You can go from A, go to C, go to B. Okay? You are now in vertex B, having visited A, B, C. You can take this edge back to D, having visited A, B, C. See that the same vertex can be reached from two different ways. So imagine that you still have, for example, 3 or 4 or 5 other vertices that has not been explored yet. Do you realize that there is going to be a lot of recomputations going on? You from AA go to some vertex, and then there are other ways to reach this vertex, and from this there are so many other ways. If you recompute the whole thing, it's going to be very slow. So we will store this information in a table. However, our table is slightly different now. Previously I only have vertex number, comma, some other integers. So integer, comma, integer. Right? Vertex number is integer from 0 to p minus 1. And then usually in the previous two examples, the second parameter is moves left. It's also integer, going from some number going down to 0. Now, let's look at this. I have a vertex number, comma, a set of visited vertices. A set. And you can have 2 power of phi such subsets. It's another combinatoric question. If you have a phi object, you want to take some of it, subset of it. There are 2 power of phi. There is a size of power set of that subset. The number of possible subset of that set is 2 to the power of phi. So getting more, right? So how many vertices are there in this DAG? N times 2 to the power of n. N is where you are now, and 2 to the power of n is the size of the possible subset of visited vertices of this vertex. How to store this? I will flash through the next few slides after this, and later your lab demo, either this week or next week, I forgot which one is which, you will be given the detailed implementations in more detail. But for now, I will show you how I can just change one line in that passage to make my code explore all possible permutations. So I will show you this code. TSP slow. So I will show you the facet first. I will flag this off. So I will read n, right? I will store the complete graph in an adjacency matrix of size n times n, right? And then I will call array, visitor to be false for all n vertices, and I'll call that vertex from vertex 0. Suppose my vertex 0 is my starting point. I want to do a tour and come back to vertex 0. Right? And my DSS rec is simply this. I will say visited u equals to true. I will visit u, and then I look at my neighbor. If I have h and I haven't visited that neighbor, I will recursively go to that neighbor. As simple as that. So let me see. Here, let me compile this. CSV flow. Then I will give the 4 times 4 test case, the same test case shown in lecture just now. Right. That person will give me, I have a path 0, 1, 2, 3, stop. Right. That's the only path that person can get. Starting from vertex 0, 0 go to 1, mark the 2 as visited, 1 go to 2, mark 2 as visited, go to 3, mark 3 as visited. By then, everything has been marked. I never flag the visitor's Boolean array to be false anywhere, right? So once it turns on, no one will be able to visit it again. Now I'm going to turn it off sometimes. Here, look at this. This one. I will say at the end of my recursion, I will do this. Visited u is false again. Just one line, right? And see what happens. The printout will be slightly funny, will be quite funny, but then it's okay. I will show you the better way, better one in the second example. Okay. See that now it becomes 0, 1, 2, 3, 3, 2, blah blah blah, longer, right? It looks funny because I don't store the path. This is like 0, 1, 2, 3, left track, and then like later 3, 2, try all possible permutation, and then back. So this contains subpaths here and there. Doesn't look nice to see, but at least it perform longer, it explore longer. So let me show you the same code, but here I edit the path. So I have a factor that tell me what is the path. If I start backtracking, the versus modify, I will insert u to this path, and then I set visited u becomes false, right? And then at the end, I say visited u equals to false, and I will remove the last item. I can call pop back or something like that. I can do that also, so that I can keep the prefix same. I'll show you that by doing so, I will be able to see all the possible permutations. Right? So if I go backtracking, I will have 0, 1, 2, 3. This is my first path. Then I will flag 3 to be visited false. I backtrack 0, 1, 2. 2 don't have other option. I take it out. 0, 1. Now at vertex 1, I can see that 3 is not flagged as visited, so I go 0, 1, 3. And then 3 can go to 2, 0, 1, 3, 2. So the second line will be 0, 1, 3, 2. The one that I shown just now here, this one. When I show you the manual demo just now, that is what I did. Okay. Don't do something funny here, please. Yoo-hoo. Okay, never mind. So here see that I'm actually really exploring all the 6 factorial, right? I fixed the first one to be 0. I explore the other 3. And since I now remember the path, I can compute what's the total weight of this path, or what's the total length of this tour. Right? So 0, 1, 2, 3 is 97, 0, 1, 3, 2 is 108, blah, 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 blah. It happens that 0, 3, 2, 1 is also 97. Among these 6, 97 is the lowest. So the answer is 97. This is the lowest possible tour. Right? So, okay, just now when I show you manual demo here, this is what the person is doing here. So this turns a phi plus e algorithm deficit into a phi factorial algorithm because I'm exploring all branches. When phi equals to 4, or here is 3, phi minus 1, I'm only do 6 times. What if I give you 10 vertices? What if I give you 10 vertices? Then factorial, just now you told me via clickers 3.6 million something, right? So you're going to see 6. No, it's actually 9 factorial because I fixed the first thing. 9 factorial is about 3 million divided by 10, about 300,000. So you will see 300,000 lines. One of this is minimum. You will see 300 lines. One of this minimum. Too slow. Okay. However, you can claim, if you are a good programmer, you can claim that the bottleneck is the printing, the output printing, because 300,000 operations, computer can do it in less than 1 second. That one was slow because you print everything. The I/O is the slowest. Okay, let's turn off the I/O. Okay. So hopefully by now you realize that the I/O is the slowest part of this thing. So I will turn off the I/O. I will compile again, then run this. Fast, right? Quite fast. After less than 1 second, I got 2576. This is the minimum. You can try all. There won't be any minimum smaller than this. Okay. However, if I give you 11, just now it's less than 1 second, right? Just now it was less than 1 second. Here I can guarantee you it's more than 40 seconds. More than 11 seconds. See? Why? Because the gap between phi 10 and phi 11 is, you are doing 9 factorial in phi 10, you are doing 10 factorial in phi 11, right? Between 9 factorial and 10 factorial, the difference is 10-fold. Right? 9 factorial equals to 10 factorial equals to 10 times 9 factorial. 10 times lower. Between test case with phi equals to 10 versus test case with equals to phi equals to 11, the gap is is about 10 times lower. This is about 10 seconds, right? So let me try 12. 10 seconds, 12 is about 2 minutes, right? So I will show this. Okay, I will talk for 2 minutes and then I will see whether it's complete. I will talk for 2 minutes. So, we will end the lecture here. You cannot go until this finishes. Okay. In 2 minutes, it will finish in 2 minutes. So what we will do next in your lab demo is to see how bitmask can be used. Bitmask is a new technique, a new data structure that can be used to represent a set of physical vertices more efficiently. And by doing that, you can turn off, turn on certain flags, certain bits efficiently, so that later you can implement this recursion quickly. So this recursion is this: if you have visited all of its vertices, you go back. Other than that, you try which neighbor gives you the minimum overall total tour length. You haven't finished. It will finish soon. Anyway, you will implement this and something else in PS7R. It will be open tonight. Whoever wants to try it, do it by tonight. You can implement this idea, start from something slow first, build up from there. You will probably need quite a significant number of time to implement that. It stopped already, 2, 4, 10. Right? So you can leave. Hopefully this demonstration shows you the power of dynamic programming, because dynamic programming can do this again in less than 1 second.